Welcome to the second session of the FDP on NEMS. I request Professor Chetan Somali to introduce our speaker, Professor Akshay Naik.
So, good morning and welcome to all the professors and participants to this MEMS course organized by SPC under the Atal scheme of AICTE. I would like to give a short introduction to our guest and eminent professor, multifaceted researcher, Dr. Akshay Naik. He is from IISc Bangalore. His academic and research milestone started with BSc Physics from Mumbai University. Thereafter, he completed his post-graduation from IIT Bombay, and then his journey drove him to Maryland University, USA for completing PhD in electrical engineering. Further, there he completed his postdoc from California Institute of Technology and has been and has worked as research engineer in California Institute of Technology for 3 years. He has 28 journal articles to his credit and 11 conference papers with several patents under his name. So today we have a very dynamic researcher who is going to give us and enlighten us in the subject of MEMS and nano sensors. So I welcome you, sir, again on behalf of SPC team and all the participants of this FDP. I request you to take on the session here forward. Thank you.
Thank you. Thank you for the introduction. Thank you for having me. Can you hear me? Can you see my slide?
Yes,
Yes, sir,
sir.
we can see your slide. You are audible also.
Okay, fantastic. Okay. So what I'll talk about is, as Professor mentioned, mechanical systems. And I don't want to call it micro electromechanical systems because in the last few years people have started using optical systems also to study these or use these devices. So maybe microsystems is a better word now. But anyway, so my name is Akshay Naik. So I come from Center for Nanoscience and Engineering. It's a department in IISc Bangalore. So this is the picture of our department. More importantly, we have one of the best facilities in the country to fabricate devices, nanofabrication facilities, and also to characterize them. And this is probably one of the top 10 or 15 in the world in academic settings. Even more importantly, these facilities are open to anyone in the country. For example, if any one of you wants to come and use these facilities to make your devices, to characterize your devices, these are open. Okay, and you can, if you have funding from DST or any other agency, you can pay pay the fees and come and use the facilities. Even if you do not have money to pay for characterization or fabrication, we do run a program that's called Indian Nanoelectronics Users Program. Okay, and we've been running this program for about 10 years now. What it is we give them three-tier training. We are in three-tier training. The first is basic training, where we have 2 to 3 days of intense lectures, where we get about 60 to 100 scientists. Then we have advanced training, where scientists come here in a batch of 20 to 25, and they undergo training for 2 weeks. Okay, on the tools, fabrication tools, characterization tools, and so on. And the third part is projects. For example, if you have a PhD, if you're doing a PhD, or if you want to do some research project, you can come here and do this research project for a month, 2 months, or however long it takes, and we will facilitate that. And the entire thing is free of charge, and it is being supported by MHRD, which is now Ministry of Education, and Ministry of Electronics and Information Technology. Okay, and we've supported about 1,000 projects in the last 10 years. And this is a joint program that we run with along with IIT Bombay. So if you're interested, you can certainly take a look at this. Okay. Okay. Let's get started. What I would like to say is, if you have questions, just speak out, and I'm happy to answer any questions in between the talk also. Okay. So, what is micro electromechanical systems? When I give talk in a in an auditorium or something, I usually ask students and audience whether they have used ever used MEMS device. And in this case, it's very hard to tell because I don't know how you will raise your hands and so on. But typically, people think they have not used it. Okay. Most people, about 80% of the people, think they've never used MEMS devices in their lives. And the fact of the matter is, almost 99.9% of you have used these devices and are using these devices on a daily basis. Okay. And the first image that you see here, right, this image that you see is the inside of an inkjet printer. Okay, HP till smartphones became very popular. This was the major market for MEMS, right? And HP was making huge profits out of this, and this is the inside of a inkjet printer. And I think a lot of you must have used inkjet printer to print things and stuff. The other thing which is now more common is things like accelerometers or gyros. Previous speaker, Professor Mohite, talked about these things, right? These are now inside your cell phones. For example, if you rotate your cell phone, you can see that the photograph that you have also rotates, right? And those are possible because of MEMS devices. There are filters and all kinds of things, but this is a major thing that you do this on a regular basis, where you rotate your phone and your image rotates, right? So you have used these systems on a regular basis. There are lots of other applications, light projection, sensors, and all kinds of things. But I just wanted to tell you that you have used this and are using this on a regular basis. My research, predominantly, I work on smaller devices, smaller than micro, and we call them nano electromechanical systems, or NEMS for short. Right? Similar to MEMS, these things can be used for a lot of applications, right? They can be used as biosensors, in mass spectrometry, force measurement, gas sensing, as oscillators. These are also not just for applications, these devices, which are very simple devices, right? For example, this one is a simple beam, right? A cantilever kind of something. These are very simple devices. They can be extremely useful to study, for example, nonlinear dynamics, right? These are fundamental studies that people are still trying to get their head around. How do these things work? How does these weather patterns evolve, and so on. Also, you must have heard recently, there is a lot of talk about quantum mechanics, quantum computing, right? There are some really fundamental questions about mechanical devices. How would the large mechanical devices, these are micron size devices, how will they behave? Will they behave as quantum objects, for example, similar to atoms, right? Or electrons or photons or whatever? Will they behave in a similar way if we make we bring in appropriate conditions? Okay. So in all these cases, these devices are used. And as I said earlier, Maybe it's better to call these systems now as microsystems, because people have earlier people used to predominantly use electrical circuits to actuate and detect these devices, these systems. But now people have started using optical systems. They use optical systems to couple to these mechanically vibrating structures, these beams kind of things, to do these measurements. So maybe microsystems is a better word, but anyway, let's move forward. Okay, so I will just give you a very brief introduction to how do we fabricate these devices, how do we make these devices. So what you can do is, and we can teach you if you do decide to come here for fabrication of your devices. You take a silicon wafer. Okay, what you can do is deposit silicon oxide on both sides of the wafer, top and bottom. Then you can strip off the top. I mean, this is optional, but let's say you strip off the top silicon oxide. Then on top of this, you deposit silicon carbide, and you can deposit any material, for example, silicon nitride also, but in this case, silicon carbide is deposited here. On top of silicon carbide, see here, we deposit something called photoresist, PR. Okay, and then we use UV light to basically expose this photoresist at specific places, for example, in this area, right? And then you can dip the entire chip in some liquid that removes the photoresist, the blue region, from the area where it was exposed to UV light. Okay, and after that you can dip it in another liquid, because the red part, the brown part is now exposed, that part is also removed. Okay, and after that you can remove this silicon underneath, and then you have a suspended cantilever which is free to move. Okay, you see this cantilever, and that's how you make a simplest of these devices. Okay, and I mean, if you think about it, if you look at mountains, right? I mean, you can see in this picture, this is just doing fabrication. Nature is doing its own fabrication. You can see these cantilevers right here, right? There are 3 cantilevers here. But the problem is we've learned from nature, but this is just random. We don't want random. We want specific shape, and that's why we use specific ways of fabricating these devices. We expose only the region which we want to etch, which we want to remove. The rest we cover it with photoresist, for example. Okay, so that's a simple explanation of how fabrication works in these cases. Okay, now the great thing about this fabrication processes is we can really make extremely small devices, very intricate devices like what Professor Mohite showed previously. Here are some of the devices that we make. Okay, so this here that I show is a monolayer graphene. It's a single sheet of carbon atoms, one layer thick. Okay, and the thickness is about 0.3 nanometers, and the length of this is, I think, about 2 microns long. Okay, only 2 microns. It's important to remember the thickness of your hair is about 100 microns or so. This is length is just 1 micron or 2 microns, and the thickness is about 3 angstroms. This here is single wall carbon nanotube. This is the diameter of this nanotube is about 1.5 nanometers. The only reason you are able to see in this scanning electron microscope image is because there is some dirt on top of it. And that's the reason you are able to see it. Otherwise, even it's hard even under the electron microscope to observe these things. This is another material which is called MOS2. We can also make devices using silicon nitride, for example, or silicon carbide, for example. Okay, so these are some of the types of devices that we make. So what I'm going to talk about today is how do we use these devices as sensors. Okay, and one of the things I would like to emphasize is how do we use these as sensors, and how do we continuously improve our sensor, right? And what goes into making a sensor, and what goes into improving them. How do we continuously ask questions to make sure we can make better and better sensors, or use the sensor for different applications. Okay. A typical sensor, you will have uh, three main things. One is the stimulus. For example, if you want to do temperature sensing, temperature would be the stimulus. And that stimulus would change some behavior of your sensor. All right. In this case, we are using a mechanical cantilever, so it might bend it. And then there would be an output, which will tell you that, look, this is the temperature that you have. All right. And for example, as I said, if this is the cantilever that we are going to use, it is free to move from this free end, and this is the clamped end, right? It's free to move here. So can we use this, for example, as a pressure sensor, right? If you provide a stimuli of pressure, what is going to happen is it's going to bend, right? These mechanical element will bend. And in terms of output, you could say, look, the displacement, how much it bends is our output. And depending on how much it bends, you should be able to extract what is the pressure that I have applied. Okay, that's the whole system. There are lots of questions in a very simple system like this you could ask to improve the sensor that you have. For example, you could say, how do you measure the displacement? And this is one of the questions, right? So in general, a lot of you, I looked at your backgrounds are mechanical engineers, right? You studied these beam structures and so on. If it's a really large beam, it's very easy to look at the displacement or the bending just by eye if the structure is big. But as you saw, the kind of systems that we make are really small, right? Hundreds of microns, a 1 micron kind of size. So as you make devices smaller, the displacement that does happen, the bending that does happen, becomes even smaller. Right? So in that case, you will not be able to use your eye. So you could say, look, I will then use optical microscope. Right? What about if the displacement is smaller than, say, a few tenths of micron? Then you could say I would use electron microscope. Right? What if the displacement or the bending happens to be less than 10 nanometers? Then people started using some electrical schemes. For example, the interdigitated capacitor that the previous speaker talked about, right, for gyros. People also started using optical schemes. Okay, so all of these are continuously improving how you do better displacement measurement. So if you have better displacement, what you can then say, I can measure smaller and smaller pressures. I have better and better sensors. Okay. So for example, you could ask a similar question. How do you make, other than improving displacement, can I make it more sensitive? Right? The simplest answer would be, look, if you make your cantilever to be more compliant for the same pressure, the displacement would be larger. All right, so that's how you make it more sensitive. Right? These are some of the questions that you ask to improve the sensor that you have. Okay, and we'll go through some of the questions, and I'll give you specific examples of these cases. Okay, so in the previous slide, I showed that there is a static displacement. You apply a pressure, it bends down. Okay, in general, it turns out that it's better to do these measurements in something that I call resonant mode operation. Okay, and the reason what it means is all these beams, mechanical structures will have infinite number of resonant frequencies, modes, and they will have resonant frequencies, right? So for example, at resonant frequency, the amplitude is maximum, right? This is amplitude as a function of frequency. At the resonant frequency, the amplitude, the motion is maximum. And if it's not at resonant frequency, the displacement is minimal. Okay. So what happens at resonance is, for the same force or for the same pressure that you apply, the displacement is enhanced by the quality factor. Okay, because the damping is low, for the same force, you have much larger displacement. Okay, that's an advantage, right? You already have improved, for example, if your quality factor is 1000, right? You have already improved your displacement measure by a factor of 1000. Okay, so that's why we use these devices in resonant mode, and these are especially useful if the devices are very small, where doing the measurements using eye or conventional methods becomes very difficult. Okay, now beyond that, the resonant frequency, the frequency at which this vibrates depends on various properties of this cantilever or beam that you have, right? For example, if you change the length, if you change the thickness, if the Young's modulus changes, right? All of these are going to change the resonant frequency, and that's the part that we will use in our sensor. That's how we will do the sensing. Okay. For example, what we'll do is we will drive this mechanical element, this cantilever, and see how the resonant response is here. How does this change in response to, say, a temperature change, right? For example, if I heat up this cantilever, how does the resonant frequency change? Right? How does the resonant response change? For example, maybe it moves to lower frequency. Initially, the resonant frequency was here at this frequency. Now, because of the heating, it has changed here. Okay. Now, if you know all the relevant properties, for example, if you know how the temperature changes the modulus or the length or so and so on, you should be able to figure out, just based on this change in frequency, how much has the temperature of this cantilever changed. Okay, even in this mode of operation, there are two ways of doing the measurement. One is I look at how much has the frequency changed, the resonant frequency changed. Okay, or the other is you say how much has the amplitude changed. Okay, and I will go through these in the next couple of slides. And these are, major ways of doing this, right? But there are lots of different reasons why you would choose one, this over this, or this over the amplitude change, right? And it depends on what you want to do, what your goals are, and so on. Okay. So let's look at these modes of operation. How do we do the actual measurements in these devices? Okay, so let's say we want to always look at change in amplitude. Okay, how does the displacement change in response to the stimulus that we provide? Okay, so this is our resonant frequency. That the resonant frequency is right here. Amplitude is maximum here. So in this case, what I will say is I will always do the measurement at a specific frequency. My measurement will always be to look at amplitude at a specific frequency. Okay, in this case, I will say I am going to pick this particular frequency and measure what is the amplitude at this frequency. Okay, and at this point, the amplitude is A0. Okay, now let's say I change the pressure or temperature. Because of that, the response has changed and the resonant frequency has moved to a different frequency. Now the resonant frequency is here. But I'm still doing the measurement at this particular frequency which I have picked. Okay, now the amplitude at that particular frequency is A1. Okay, that's that change in amplitude that has happened because you have changed the temperature or pressure or whatever sensor you have. Okay, so in general, we do not do the measurement like this. What we do is we continuously monitor amplitude as a function of time. So in that case, we have amplitude here and this is time. So what we'll do is initially the amplitude was A0, but because we change the temperature, now the amplitude is A1. Okay, obviously there will be some slow response of some time taken to respond from A0 to A1. Okay, and this part will depend on your measurement system and how the device is and so on. Okay, similarly, you can do the same and say, look, I will not look at the amplitude change, I will look at the change in resonant frequency. So in this case, what I say is, I will always try to find out what is the maximum amplitude and at what frequency is that happening. Okay, in this case, I say, look, this is the maximum amplitude and this is happening at this particular frequency. Now I change the temperature, this has moved, the amplitude is maximum here, and that frequency is F1. Again, we do these measurements in time domain. The frequency versus time looks something like this. Initially, the frequency was here, but now because of the change in temperature or pressure, the frequency has increased, and you get something like this. And obviously, the frequency can either increase or decrease depending on the type of measurement that you're doing. Okay, okay. So let's get started with actually doing the measurements and making some of these sensors. Okay, so the principle, the reason these things work very well as sensors is very simple. Okay, if you ever seen a guitar string, the principle is exactly the same, right? What you have is the resonant frequency of these devices depends on the mass of these strings or these devices. Okay, inversely proportional. So if you've seen these guitars, they have different thicknesses, right? The thinner one vibrates at a much higher frequency than the thick one, right? That's what this is indicating, right? And the device is just vibrating like this, right? At the center, right? If it's a beam, at the center, the displacement is maximum. At the clamped edges, the displacement is 0. Okay, and the same thing happens whether it's a guitar string or a string or a beam that is made using monolayer graphene or a silicon nitride or aluminum or silicon carbide. Doesn't really matter, and this pretty much holds in all of these cases. Okay, and we will use this to do our detection, right? So the principle of mass sensing remains the same. So what we'll do is, let's say you have a guitar string, right? You tuned it to certain frequency, okay? And you know the mass of this guitar string. And let's say your son or daughter comes home and puts a chewing gum on top of this, right? On top of the string, the resonant frequency has changed because there is added mass, right? The frequency is changed. Now, if you want to find out the mass of your chewing gum, right, all you need to know is this change in frequency, and you should be able to figure out what the new mass is, right? From the new mass, you should be able to figure out what is the change in mass that has happened because of your chewing gum. It's as simple as that. And we do this again in real time. You look at frequency shift, and based on this frequency shift, you should be able to figure out what is the mass of, the chewing gum in this case. In our case, we look at gas molecules, protein molecules, and so on. Okay, again to emphasize, so if you know the frequency shift that has occurred, okay, you already know the mass of your device, you already know the resonant frequency of your device, you should be able to calculate the added mass. Okay, so it's as simple as that. The only condition in this case to get this equation is that this added mass must be much smaller than the mass of your cantilever or your guitar string or whatever. Okay, that's the only condition to make this approximation. The only difference between guitar string and to a MEMS device or a NEMS device is this sensing has been taken to extreme levels. Okay, and what I mean by that is, as you make devices smaller and smaller, the minimum mass that you can measure improves dramatically. For example, if some of you have used evaporators, right? Evaporators, they have something called quartz crystal monitors. Okay, those those work on exactly the same principles. Right? They have a vibrating element As you evaporate material, it deposits on those elements, and because of that, resonant frequency changes, and you do the detect, how you tell how much material you have deposited. In a lot of these cases, in these cases, you can see the resolution of these crystal monitors is about nanograms, 10 to minus 9 grams. As you make devices smaller and smaller, you see that the minimum mass that you can measure improves dramatically. Even when you go from, say, a MEMS device, which is, say, hundreds of microns, to a NEMS device, hundreds of nanometers. The, the resolution improves dramatically, right? For every one-tenth reduction in dimension of these devices improves the resolution by about 1,000 to 10,000 times. Okay, so there is a really dramatic improvement. And to give you a sense of what this 10 to minus 24 means, that's individual hydrogen atoms, for example. Right? In fact, in experiments, in idealized experiments, people have shown that they can actually measure, in principle, hydrogen atoms. In fact, in other measurements, people have shown that you can actually detect individual biomolecules, proteins, right? And that's a really great achievement that have been possible because of reduction in size of these devices. Okay, let's make a gas sensor. What we'll do is we'll make a gas sensor, we'll make a biosensor, we'll see how to improve them, and then we'll also try and see if we can make a detection scheme to detect individual biomolecules. Okay, let's look at gas sensors. So here is our cantilever. Again, the resonant frequency depends on the mass. To detect the gas, what I'll do is I'll spray in the gas, okay, and this gas will deposit on our cantilever. Obviously, the mass has changed because the total mass is now a combination of this yellow part and the black part, right? So the new frequency is different from the old frequency. So you again measure this change in frequency. That's great. So the question that you ask is this a good sensor? And the answer is not entirely clear, right? And at the first instance, I would say, yes, it's a good sensor because now I can detect this yellow gas that I sent in, right? But if I ask the question, sure, you detected that yellow gas, but how do you know it's actually this yellow gas and not this red gas, right? Who knows? Would you be able to tell me which gas landed on your cantilever? And based on this experiment, it's not possible, right? It's almost impossible to tell. So if you are only interested in trying to figure out how much of the yellow gas, and you are always going to send in the yellow gas to the cantilever, then it probably is a good sensor, right? But I can always improve this cantilever by somehow making it possible for us to detect even the red gas. Okay, can we do that? Okay, so what we'll do then is, so let's say we want to specifically only capture yellow gas. Okay, that's our goal now. We don't want to capture red gas. So what we'll do is we'll take the cantilever and functionalize it. By functionalize, all you have to do is maybe coat it with some chemical, which will predominantly, right, capture the yellow gas, and maybe a little bit of red gas, but predominantly yellow gas. Now you do the measurement again, okay? So you sprayed it, again it sticks to it, the resonant frequency changes, again you see a frequency shift. Now, this is a slightly better gas sensor, right? You ask again the question, is this a good sensor? It's better than the previous one, but there are two things that you have done. One, you added this green part to your cantilever, right? Which means the size or the dimension of your cantilever or your sensor is now bigger. As I said earlier, if you make devices smaller, they are more sensitive in general. If you make them bigger, they are not as sensitive. Just by adding this, right, you compromised on the sensitivity of your sensor. Okay, that's one part. The other part is, sure, the cantilever absorbs this yellow part predominantly. But what if, even if it absorbs a very small quantity of red gas, it will still absorb this, might absorb this much portion of this entire red gas and will still produce the same frequency change. You still do not have a way of identifying whether you absorbed this much gas of yellow or a very big portion of red. Right? You have no way of knowing. Okay, so can we improve on this a little bit more? Can we do better? Okay, so what we'll do is, so one way of doing this is to say, I will try to collect a fingerprint of these gases, right? What we'll do is we'll have an array of cantilevers and we will functionalize each cantilever with a different chemical. Okay, and when the gas comes, each cantilever for the same gas, each cantilever responds differently. For example, this cantilever bends or changes resonant frequency by a large amount. This one doesn't change much. Okay, let's try to do this. So what we'll do is, as I said, each cantilever will have a different response, and this combined response of all these cantilevers with different functionalizations will be considered a fingerprint, and I'll show you how. Okay, so here is the array of cantilevers. We have functionalized each cantilever with a different chemical, okay, and we will monitor the resonant frequency of all the devices, all the cantilevers. Okay, here is the resonant frequency as a function of time. Okay, let's send in gas 1, which could be yellow gas, for example. So the first cantilever, this one doesn't change much. Maybe as the gas comes in, the resonant frequency changes a little bit and goes back up. The second cantilever, and all the cantilevers are shown here. The second cantilever, maybe the resonant frequency changes by a significant amount. Third, not so much. Fourth, a lot. Fifth, a little bit. Okay, and if you can do the same thing for gas 2. In this case, the fingerprint will be entirely different. For example, cantilever 3, right, this particular cantilever might not respond as much to gas 1, but might respond by a large amount to gas 2. Okay, similarly, cantilever 4, gas 1, in response to gas 1, the frequency changed a lot. In response to gas 2, it did not change much. Okay, so what we'll do is we will use the ratio of all these different cantilevers as a fingerprint, right? So for example, if the frequency shift of first cantilever was just 1 hertz, second was say 7 hertz, third 2 hertz, fourth is 9 hertz, and fifth is 4 hertz. The fingerprint is the ratio of these 1, 7, 2, 9, and 4. Okay, so if you increase the amount, say let's say you double the amount of gas 1 that you send, the only thing that will happen is the fingerprint will now show that as 2, as to 14, as to 4, as to 18, 8. Right? But the ratio remains the same. Okay, and similarly for gas 2, right? The fingerprint is entirely different. Okay, this is one way where you can try to figure out which of the two gases you're detecting. Okay, and you can ask again multiple questions here. The simplest would be, would this work? And the answer is not entirely, and I will leave it there. Okay, and people have figured out different ways of making sure that they can use this kind of system to do gas sensing, but I will leave that as a brain scratcher for you guys. Okay. Okay, so we talked about gas sensor. Let's next talk about biosensor. By biosensor, what I mean is typically we are interested in what is happening in our body. Right? This is for all kinds of reasons, to detect diseases and so on. So let's say we have a cell, we are interested in what are the biomolecules that are present in the cell. Okay, and let's just assume these are the biomolecules that are present in the cell, and we want to do the detection of one of these biomolecules, right? Because let's pick this one, the hard one, right? So how do you do the detection? What you can do is take these, right, and pour it on top of your cantilever. Right? Take the contents of the cell, break the cell contents, take those contents, put all of these onto your cantilever or your sensor. They all deposit there. Obviously, it bends down. Is this a good sensor? The answer is no. I mean, the only thing you have shown is that it can detect something. But what you are detecting, that information is absolutely not available. Right? You don't know whether you've detected the hard ones or the sun kind of things and so on. Okay, so what you can do is, again, you can do something similar to what you did previously to do functionalization. In this case, you can come up with all kinds of molecules which will capture only specific type of molecules. Right? These are antibodies or something that you can put on top of your cantilever, and they will capture only or predominantly these heart cells. Okay, so for example, they capture. Okay, so but there is always a chance, right? There is always a chance that a little bit of other molecules will also be captured. For example, in this case, it's predominantly captured the hard kind of things, but it has captured one, the sun. Right. So you might say, the question again is this a good sensor? And answer could be yes, but it's only a could be. The reason is this. Let's say these things, the functionalized material, are going to help you specifically bind the biomolecules that you want. It's going to capture only this one 99% of the time, and only 1% of the time is going to capture some wrong element, wrong biomolecule. Okay, and that works very well. That's great. In that case, it's really good. So if there are 100 hearts and 100 sun kind of things, then it's great, right? You are going to predominantly capture hearts, and maybe one out of 100 will be the sun. Now that's great. But what if there are only 100 heart kind of things and 100,000 suns? In this case, what you would see, even though the capture cross section is only 1%, or 1% of 100,000 is really large, that's about 1,000. Right? That specificity that you said, look, I will predominantly capture only this, is lost. Okay, now there are more these kinds of structures that are captured on the cantilever than these ones. So in this case, it will not be a good sensor. And in a lot of biosensing, right, the specificity becomes extremely important. And the reason is this. For example, at the onset of a disease, right, for example, certain biomarkers might show up. And the number of these biomarkers that do show up is usually very small compared to all the other biomarkers that are present in the cell or in the body. Right? If you want to do the detection at early stage of disease, you really have to figure out how do I detect these very small number of biomolecules, and the specificity in that case becomes very important. Okay. Okay, so the other question that you could ask is, look, fine, we will do, let's say the specific binding is still working and it's good enough for us. The other question you could still ask is, what is the minimum number of biomolecules do I have to capture before I can see any signal? Can I capture just one biomolecule? And will that be enough for it to change the resonant frequency, or will it bend enough? Okay, that's another question that you could ask. As I said, what is the minimum number of biomolecules you can detect? Because if you detect smaller number, you will be able to do the disease identification at an earlier stage. For example, in cancer, right? The earlier you detect, the more the chances are of a recovery, right? The other question you could ask is, look, I've built this biosensor. How do I use it? And it's a very simple question, but it's extremely important. For example, I could say, look, I have made a chip, has these cantilevers. What I can do is pick it up with hand and dip it in bio solution. Okay, is this a good enough method? The answer is no, right? Because the reason is the humans are prone to errors. Okay, so maybe the better way to do it is some kind of microfluidic chip. Okay, and this chip is about a few centimeters wide and few centimeters long. Okay, and here you can see there are channels here, right? So there are channels that go from this end of the chip to this end. Okay, and what you can do is you can send your analytes, your liquid, through these channels. You flow in from here and it comes out from the other end. Somewhere in the middle of these channels, you can stuff your cantilevers, which are going to do the detection as we talked earlier. Okay. So again, you will have on top of these cantilevers, you will have probe molecules which are going to capture these target molecules, and you will see some bending, and that will help you identify how many target molecules were there in your cell or in your body or whatever. Okay. Now, will this make a good sensor? And again, the answer is not clear. And again, it depends on what you're trying to do. Okay, one of the first things that you will realize is because you're going to do these measurements in liquid, in a flowing liquid, the damping will be large. Okay, which means the quality factor will be very small. And we talked about the advantage of having a large cube, and that advantage is almost lost here. Right? That is one problem. And the question is, can you solve that problem? Right? If you can solve it, you obviously will be able to do better measurements. The other question is, sure, you have put in these probe molecules, and the target molecules are supposed to come and stick. But will they come and stick? Right? In general, what happens when you make channels very small, the molecules do not like coming close to surfaces. Right? So will enough target molecules stick onto these things? Right? Those are the questions that you have to ask. How do you make sure that they come there? Right? Okay, let's try to see if we can solve at least the quality factor or the damping problem. Okay, so people have done this. So we said, look, if you put the cantilever in the liquid, the damping increases, the quality factor decreases. What if you made a channel inside a cantilever? So what if the liquid is inside the cantilever as opposed to cantilever being in liquid? Okay, so in this case, what they have done is they have made channels inside this cantilever. The blue line is a channel, right? Here are the zoomed in cartoon images, right? So you have the liquid flowing in this region. So it comes in and flows out. If the number of biomolecules that are of interest to you are very small, you have certain frequency. As the number of biomolecules of interest increases, the frequency decreases. Okay, so in this case, what you have done is you have solved, at least to a large extent, the problem of having large damping. In this case, you can manipulate these structures as well as how the liquid flows, what kind of liquid flows, to improve the quality factor. I think if I remember right, the quality factor that these people achieve is close to, I think, 1000, which is very good. and the liquid is still flowing through the liquid through the cantilever. But there is a problem, right? While you are increasing the quality factor of your cantilever, while allowing for liquid flowing through, what you have to compromise on is the size. For example, if you want the liquid to reliably flow through these channels, you would want the channels to be, say, about hundreds of microns. What that means is the width of these would be, say, about 500 microns or a millimeter. In that case, the length of these would be, say, 10 millimeters. So you are really in millimeter size range. So you have lost out on the sensitivity part that you gain when you make devices smaller. Okay? Okay, so let's go a little bit further and see what else can we think about in terms of mass sensing. Okay, in all of the cases that I talked about, both in gas sensing as well as in biosensing, we assume a uniform coverage on top of cantilever. Okay, and what we say, the response, the frequency change is dependent on the amount of mass that I have put on the cantilevers. Okay, so for example, the frequency change that I do get is dependent on this mass that I have put on the cantilever. What if the added mass was point mass? And I think a lot of you have studied this, right? Uniform loading, point loading. The response must be different. Right? It's not possible that it gives the same answer. For example, if I take a biomolecule or a particle or whatever, and I added that point mass specifically at the free end, what is the frequency shift that I get? Of course, I will get something. But will it be the same when I place this here in the middle of the cantilever? Will it be same if I place it at the fixed end of the cantilever? And the answer obviously is no. I mean, it will change, right? And this is a problem. For example, as you reduce the amount of gas that you send in, right? Initially, you were sending a lot of gas. There were millions of gas molecules. But let's say you reduce the amount of gas that you send in, or you reduce the number of biomolecules that you are sending in, right? You will not have millions of biomolecules for you to have uniform coverage. You will have individual molecules that are going to stick to the cantilever. And that individual molecule will produce a frequency shift, right? And whatever frequency shift that I get here is not giving me a correct frequency shift because it will depend on where it landed, right? So there is a problem there. And this equation is not exactly right. The correct equation to say is the frequency shift not only depends on the mass of your particle, right, this mass, it also depends on where this lands. If it lands here, the frequency shift is maximum. If it lands here, the frequency shift is minimum. Right? So that position dependency is included in this part of the equation. Okay. But okay, let's look at it a little bit more carefully. Okay, so in gas sensing, again, you have uniform coverage. Okay, and what that means is this is constant, so this doesn't really matter. Okay? Whereas if you have point loading or point masses, you have to account for this part. Okay. So for example, let's consider the fundamental mode, right? The first mode of vibration. So it's the displacement is largest at the center, okay, for this beam. So if the particle lands here, the frequency shift is maximum. If it lands here, the frequency shift is minimum. If it lands somewhere in between, obviously some intermediate value of frequency shift. So this frequency shift depends on the position along this beam or cantilever, right? Okay, but the important thing to remember is even though we have lost out the information, we don't have this information. The important thing to remember is that we can detect individual biomolecules, and that's a huge advantage, right? We have capabilities now to detect individual molecules. The only thing that you have to ensure is you have to make devices sensitive enough. And the way you make devices sensitive is to reduce the size of the cantilevers or the beams that you have. Okay? So let's see if we can do that detection. Okay? So before we get there, let's try and see why we want to look at individual biomolecules, right? Okay, so your cell has all kinds of things and you obviously are interested in these things. So one of the things that people are interested is what kind of proteins you have in your cell, in your body. Okay, and proteins do all kinds of functions. Here are some of them. I mean, let's just say we are interested in defensive proteins. Now, why? Because it helps us protect against viruses and bacteria. Right? Viruses are in vogue now, so we need to know whether I will be protected against certain viral infections. A typical cell, and it will also tell you whether you will get a certain disease or not. Okay, a typical cell, for example, or I think this is for bacteria, it will have all kinds of proteins with different masses. Okay, and the number of these proteins, for example, this 20 kilodalton protein, there could be a million. Okay, the 100 kilodalton protein could be a few hundred. Okay, and if you don't know what kilodalton is, it's about 1,000 hydrogen atoms. That's the mass. Okay, so let's say we do want to do detection of these proteins. So how do we do this? How do you say I have this particular protein? Okay, and in general, the way to identify proteins is by looking at their mass. Okay, if I can detect the mass of a protein, in general, I am able to tell what that protein is. Okay, I'm simplifying this to a large extent, but that's the essence. Okay, and the question is, can we identify proteins by looking at their mass with our devices? Okay, so we'll do that experiment. We'll do that experiment to detect individual biomolecules. Okay, so again, as we've already done a few times, we will look at frequency shift as a function of time. Okay, and we have a cantilever or a beam. If you do not send any protein or biomolecules, you will see that frequency doesn't shift. With time, it stays the same. And there are obviously some background fluctuations, but more or less it doesn't change. But now we send in some protein molecules. Okay, this is our beam. We are sending in these protein molecules. They are landing on this beam. What you will see is that there are these jumps, right? Frequency changes that are happening. And each of those frequency changes is because of one single molecule, like one molecule coming and dropping on our device. Okay, and you can change the protein molecule, and we've done that, and you can see that again, you will see that there are these jumps. This is one type of protein, this is another type of protein. And again, each of these jumps, this is one single molecule, not thousands, just one. Okay, but the question that immediately arises is, look, this is the same protein, but you can clearly see the frequency shift is completely different. For the same protein, it must have the same mass, right? Why are the frequency shifts different? And we already talked about it. And there are lots of other reasons why the frequency shifts are different. But from the mechanical system point of view, the reason is that it could be landing in the center of the device, center of the beam, or it could be landing at the clamped end of the beam. All right. So depending on that, the frequency would shift. Okay. So we have detected single molecules, and that is seen from the frequency shift, but we have not detected the mass. We cannot calculate the mass. And the reason is this. we have a frequency shift that we are seeing, but we don't know two things. One is the mass of the biomolecule, the other is the position. So if you solve simultaneous equations, you know if you have one equations and two unknowns, that cannot be solved. Right? But on the other hand, if I have two equations and two unknowns, that equation can be solved. Okay, so the only two unknowns are the mass of the particle, biomolecule, the position of the particle along the length of the beam or cantilever. Okay, but how do I get delta F1 and delta F2? How do I get two frequency shifts? Well, it's quite simple. What you do is, till now we've only been using the fundamental mode to do the detection, the first mode to do the detection. We can use the first and second mode, right? As we said, look, if the particle lands right here, the frequency shift is maximum for the first mode because the displacement is maximum here, right? And if it lands here, the frequency shift is not that large, right? You will not get much of a frequency shift. But let's say the particle lands here, the frequency shift is maximum. But it's the same beam, right? This beam and this beam are the same, only the modes are different. The frequencies are different. So if the particle lands here, for the first mode, the frequency shift is large. But for the second mode, because this point, the center point of the beam, for this mode, there is not much of a motion, the frequency shift is very small. Okay, so anyway, you have two frequency shift, one for frequency shift of mode 1, one for frequency shift of mode 2, and using these two equations, you should be able to calculate these two unknowns. Okay, so here's so just to give you an idea, so the position dependence, right? This is for mode 1, and this phi, this is this function. For mode 2, it looks like this. Okay, and if you look at something what we call responsivity, how responsive is this mode to a particle landing? For the first mode, again, the responsivity is largest if the particle lands at the center, right in the center. But for mode 2, the responsivity is 0 because there is not much motion that's happening here. Whereas if it lands here, for mode 2, it is largest, or here. But for mode 1, that's not the largest, it's somewhere here, right? Okay, so what we'll do is we will look at a single device, but we will use two modes to do this detection. Okay, so let's try and go through it step by step, how we are going to do this. Okay, so here's our cantilever or our beam. And let's say I take a particle and I place it right in the center. Okay, for mode 1, that means maximum frequency shift. For mode 2, that means 0 frequency shift. Okay, here I have plotted frequency shift of mode 1 versus frequency shift of mode 2. For this particular case, this is maximum, so it will be here, maximum. This is 0. So the point will be somewhere here, so I'll do that. Okay, let's say I move the particle, the same mass, it's the same mass even though I've used different colors, I move it to a slightly different position. So what happens? Now the frequency shift for mode 1 is slightly lower than what it was before, but for mode 2, frequency shift has increased a little bit. Okay, so you place that point here and you go next at this point. Right? For mode 2, the frequency shift is maximum. For mode 1, the frequency shift is somewhere here, not 0. Right? So maybe somewhere here. Okay? So there you go. You can keep doing this, right? You can keep going further, right? And you will see the frequency shift is reduced now. So F2 will be here. And then you keep going and you right at this point the frequency shift for both the modes is minimal, right? So for the same mass, it's a particle of same mass, you have different frequency shifts for the two modes. Okay, what it means is you have a curve of same mass, right? So you have the same mass, depending on the position along the length of the beam, you will see this particular combination of delta F1 and delta F2. Now, if I change the mass of the device, mass of the particle, right? Let's say I say this was 1 kilodalton. Let's say I try the same kind of experiment with 900 Dalton biomolecule, right? In that case, this is the curve, right? Equimass curve in some sense, right? Or if I increase the mass, all the points that lie on this curve will have the same mass. The only difference is the position. Okay, so once I have this entire curve and I can calculate this mathematically, okay, what I can then do is go ahead and do the measurement. When I do the measurement, I will see two frequency shifts, delta F1 and delta F2. And I say, look, I will place that delta F1 and delta F2 in this graph. Say, for example, here. If it lands here, I already know if it lands here, it's 900 Dalton. I know the mass. In fact, I can go ahead and back calculate the position, exactly where it landed here. Correct? So that can be easily done. Okay, so I'll show you the measurement itself and what happens. So this is a beam. It looks like a complicated design, but you can see that there is a beam here right in the center. Okay, that's the vibrating element. That's the part that's changing. And on this side, you have frequency shift of mode 1, frequency shift of mode 2. Right? So, and you can see that for the same element, for the same biomolecule, the mode 2 frequency shift is this much, mode 1 frequency shift is this much. So obviously the two frequencies are changing by different amounts. Okay, and using this, and as I said, if you have two equations and two unknowns, I am able to calculate the mass of biomolecule that has landed. So for example, I can take this frequency shift and this frequency shift and calculate what the position is of the biomolecule along the length of the beam. I can calculate what the mass of that particular biomolecule is. Okay, and based on that, you can get a spectra. Right. The reason this spectra is important is then it tells you what all proteins are present in your body. Right. It's as simple as that. Okay. And people have taken this concept much further. For example, they have done all kinds of detection on, say, in this case, they have taken virus capsids and try to figure out whether they can distinguish the virus with and without the DNA molecule inside it. So if you know anything about virus, the virus consists of two major parts. One is something called capsid, or that is the protective wall that it has, and inside this capsid there is DNA or RNA inside. Okay, if the RNA is not there, it will not reproduce, right? So they are able to, in their measurement, they are able to distinguish between virus capsids that are, that have DNA or RNA inside and that do not have these DNA or RNA inside, right? So that's the kind of sensitivity level people have been able to take these devices to. In addition to, there are lots of other applications, and I'll not go through these in much detail. So for example, force sensing, right? What they do is they make an array of these cantilevers. In this case, these are vertically standing cantilevers, right? So you can see these cantilevers just sticking out from the chip. And then they take biomolecules, right, and cells and put it on them. You can see that these cantilevers in this picture, those are very short. In this picture, those are very tall. right? So the compliance of these is different from the compliance of this. And they are trying to study how cells react to the stiffness of these cantilevers. And it gives you an idea of what is happening to the cell, right? For example, if you want to study how cells react to cantilevers with and without medicine, right? For example, let's say if you want to know the answer, look, the cantilevers are holding on, the cell is holding on to these cantilevers very well. In this case, maybe this cell is healthy. Now, let's say I send in some poison, right? In this case, what happens to the cell? Is it still going to hold on to these cantilevers, or will it let go? And at what concentrations does it really lose its ability to hold on to these cantilevers? Also, as I said previously, these devices have also been used in all kinds of fundamental studies. One is the question of, can I use this mechanical device as a quantum mechanical object? Right? Just like people say, look, this atom is, a quantum mechanical object. Can you say the same thing about our beam? Right? And there has been a lot of really interesting studies even in these cases. I'll not again not go into details. You can see that the information can be transferred from an atom, artificially atom, to a mechanical device. So the atom gives out energy, and that's transferred to a mechanical resonator, and then the mechanical resonator in turn gives it back to the two-level system, and the back and forth continues. So there have been really a lot of interesting stuff even in these cases. Okay, so that's all that I had. Again, if you have a chance to come to our facility, maybe once the COVID is subsides, please do come and visit our center. A lot of really famous personalities have come to here. Obviously, Ratan Tata, ex-President Kalam. We also have Adam Gilchrist came here. Obviously, Prime Minister Modi visited. President Kovind also visited some time ago. You can already see other ministers here. So it's a really vibrant center, and if you come here, you will see why we are probably the best nanotechnology center in the country. Okay, so thank you. I'm happy to take any questions if you have.
Thank you, sir. Any questions? Yeah,
Sir,
please.
I have one
Yeah,
question.
yeah, please go ahead.
Yes.
Sir, you have shown the particular graphs over the things, whatever we have measured with the biosensors and the liquid channels. So, what I want to ask is, you have come across with the 3 to 4 configurations. In which configuration we have taken this particular observation, and we have taken that particular two different things of equations which we have formed along the discussion.
You are talking about this particular slide?
Yeah, no. What I am asking is, which method we have followed for making to solve the particular two unknowns and two known equations.
Ah, okay. So I see. This okay.
Yeah, this equation, this one, sir.
This, yeah, I understand. Right. So in this case, right, we do not. You see, one of the things that we have to do if you want to detect biomolecule, as I said, is that you have to make devices very small. Okay, what that means is if you do any functionalization, the mass of the device increases, and we cannot have that.
Yes, sir.
Okay,
Yes.
so what we do is we do not put any functionalization on this device. There is no functionalization. So it is a very small, I think the device length is maybe about 10 microns or maybe 15 microns. Okay, and This is done in ultra high vacuum. So for example, I showed you gas sensing, biosensing. Biosensing is done in liquid. Gas sensing is done in ambient air or whatever. We cannot do these kinds of sensitive measurements in air or liquid. Again, because of two reasons. One, the quality factor degrades very quickly for these small devices if you are in air or liquid.
Okay.
And we want very high quality factors. We don't want any damping. And that's one reason. The other reason is if you are in air, there are gas molecules everywhere, right? You will deposit those gas molecules on these devices and not be able to see the effect of the biomolecules that we are interested in. So what we do is we make a specific measurement system which is ultra high vacuum and which only lets a few molecules at a time into the system, right? And unfortunately I don't have that picture here. Let me just see if I have.
Sir, and I have one thinking also that if we have that particular spectrum of the molecules whichever we are using, so that we can detect the particular frequency changes whichever been recorded in online, whether it is possible or not, sir.
Sorry, say that again. I didn't understand this question.
Yeah, we might have some mass spectroscopy analysis of any biosystem or any gas system which we are tend to analyze, so that we can have that particular mass spectroscopy uh, data, and whether we can match that particular data into our real time measurement or not, sir.
Yes. So, for example, if you do the measurement, right? If you see that, for example, in this case, if you see that I have this frequency shift and I have this frequency shift, and based on this, I can tell this is the mass. Okay, and at this point, you could say these are the possible biomolecules that this corresponds to, because not every protein will have this mass. Okay, now the question is, how confident are you that this is this particular protein? That's a very hard question to answer. For in general, what happens is, what people do is, once they know that this is the mass of the protein, okay, they will go ahead and do an additional step where they break this protein into peptides, okay, smaller particles, and look at the mass of those peptides. Okay, once you know the mass of those peptides, then you know what specific protein this is, because a protein will break into certain peptides. Okay, so once you know the mass of all the peptides as well as the mass of the protein, you should be able to tell what specific protein this is, and this can in general be done in real time.
Okay, sir. Okay. Then after releasing of some energy, the peptides mass will be varying. So depending upon that, we will be finding out whatever the molecule has been seen. Right, sir?
Yes, yes.
Thank you, sir.
There are two questions sir in chat box. Two questions from Prachi was. First question is how to measure frequency of cantilever and what is device used for?
Okay, I will try to answer the first question. When you say how do we measure the resonant frequency, there are many different ways. For example, let me okay, so let's look at this. Okay, so what you see, and maybe it's not very clear, what you have is a beam which is really long, okay, and then you have a capacitor, you have a gate right next to that beam, right? It's very hard to see, but there are two things. One is the beam which is clamped at this end and this end. The other is a gate which is connected to this. As the device vibrates, and this is just one way of doing, as the device vibrates, it gets closer to this gate and farther away. So it basically comes closer and moves away. Okay. At resonant frequency, this motion is maximum. Okay, what that means is at resonant frequency, the capacitance change is maximum. Okay, so by monitoring the current flowing through the device or by looking at the change in capacitance, you should be able to tell at what frequency you have the resonant frequency. Okay, for example, you sweep the frequency and drive this beam, right? You drive this beam at different frequencies and see at what frequency is the motion maximum. Now that's one way of doing this. Okay, but if you want to think about it, it's very similar to, for example, vibrate a string, all right, and it predominantly vibrates. You can see that it's kind of vibrating at the resonant frequency. Right? That's pretty much what we do. We try and see, we send forces of different frequencies. At the resonant frequencies, the displacement is maximum. And the measurement can be done either capacitively, piezoresistively, piezoelectric, optical detection. People have done all kinds of measurements on these devices. Okay, so that's the first question. The second question is which device is used. I don't completely understand what that means. In the mass spectrometry measurements where we detect biomolecules, the device is made out of silicon carbide or silicon nitride, in some cases even silicon. But in general, it doesn't really make much difference. For example, we could have used a carbon nanotube to do those measurements. There are certain advantages, there are certain disadvantages. We could have used graphene, we could have used any other material, right? But the material in itself doesn't make a huge difference. Obviously, there is give and take in no, there is always a compromise between one material and the other. I hope that answered the question.
Sir, I have a question. Am I audible?
Yes, please go
Yes,
ahead.
yes.
Yeah, sure. Sir, how we can check, you are mentioning about this bioanalytes or the markers, how we can check that whether they correctly binds at the correct exact point. So if you are using in a cantilever, how we can check that whether it exactly binds.
I don't, sorry, say that again. I couldn't hear you.
How we get to know that in the cantilever, if you are using a biomarkers or bioanalytes, how we get to know that whether they bind in the correct location. Because like if you're going for viral studies or any other cancer studies, we have to consider some correct markers to bind that, right? So how we get to know that whether it binds on the correct location?
I mean, that's a hard question, but the way to do it, I guess, is to you to have these what are they called, functionalization only at specific points. That is the simplest way. So if for example, uh, if you functionalize the cantilever only, then it will bind only at those places, right? But I mean, that's let me just go to this slide. Right. So, for example, if you functionalize only the cantilever and only those areas will the biomolecule will come and stick. Now, is it possible the biomolecules go and stick somewhere else? Absolutely. But you are not doing the measurements there anyway. So it doesn't really matter that much. But you could say, look, but any molecule that sticks in place that you don't intend, that's a loss of the material. That is absolutely right. You could probably coat the surrounding with some other chemical so that things don't stick there. I'm sure there are a lot of different ways of doing this, but for us, the easiest way is to put the functionalizing material only on the cantilever and then hope that that's exactly where the biomolecules of interest come and stick.
Do you have any device or an instrument that we can observe that, whether it's
Observe where it sticks.
yeah, where it sticks?
Because these devices are so small, right? And I usually don't work with biosensors. I usually work at sensing of individual biomolecules. Um, Figuring out optically where the molecule has landed is very difficult, right?
Okay.
But as I said, if you do the measurement of two modes, I can tell where the biomolecule has landed along the length of the beam. If it lands away from the beam, I cannot tell. But on the
Okay.
beam, I can tell you the location, okay,
Okay,
just
sir.
by doing the measurement,
Okay.
right? But not by observing. No, you cannot see anything there.
Okay, sir. Thank you. Thank you, sir. Thank you so much.
Sure. Any other question?
Any other questions from participants? That's all, I think, sir. One more
Okay.
question is there in chat box. You can refer to. The one question in chat box:
Which
which material
should be
should
used
be
to
used
detect.
to detect the biomarkers for lung cancer?
I see. I mean, that I don't know anything about specifically about lung cancer, but yeah, I'm sorry about that. I don't know about lung cancer specifically, but I'm sure there are protein biomarkers or other biomolecules that show up because of lung cancer. For example, a lot of people are doing not mass spectrometry, but they are doing gas sensing, breath analysis, and looking at volatile organic compounds that are coming out in your breath. And based on that, they are trying to detect lung cancer. But I specifically don't know of the biomarkers that show up for lung cancer. I'm sorry.
Any other questions? I think that's it, sir. So thank you very much, Professor Akshay Naik, for giving the valuable time and explaining the names and simplifying the sensors. It was a wonderful session, wonderful to hear all these things from you. So thank you very much, sir.
Thank you so much for having me. It was
Thank
very.
you, sir.
Thank you so much. Okay.
Thank you, sir.
Thank you. Bye.
Is there any feedback, sir?
Feedback link will be shared in the chat box and in the WhatsApp group. Next session will start at 2 p.m. and the next session is of Professor Prasanna Gandhi from IIT Bombay. Please log in 10 minutes before to avoid the last minute rush. It is very important session. Please don't miss it.